Yeah, I think we should sit.
Okay.
It's a heavy topic, so we should sit.
I've been walking around so much today. Okay. I am happy just to sit down.
Yeah. So anyway, the topic today is CFD. Who knows what CFD is? Well,
this is good.
Few people. So let me start. So usually we talk about CFD around a car. So these are all the things that when you're driving the car you don't see, but it's happening. So the flow around the car generates the force that you see when you're paying your gas or you're paying electricity when you are filling the tank, because the force that the air is exerting on a car or a truck or any vehicle removes the energy from reduces the energy efficiency. The other thing that is important here is that when you're simulating the aerodynamics, this is what we usually call computational fluid dynamics. It's computationally very intensive. So there are two applications in automotive industry that take the most computational power. One is crash simulation, and the other one is what you see here. So there are several things that are quite interesting here, at least for me. It's does anybody know how much energy does let's say the leathering on the tires take away from your fuel economy? Anybody willing to bet? So it's usually about 5 to sometimes maybe even 10%. That leads to about 2 to 3% of fuel economy goes for those leathers that you see on your tires. So this is complicated. It's important. And maybe Neil, you can share with us what are you doing here with CFD and what is NVIDIA doing, and maybe we do it on the next slide.
Yeah, sure. Yeah, computational fluid dynamics, and I guess more broadly, computational engineering is what is becoming now the key trend of simulating everything before manufacturing. And I think that point when you need to do physical testing is moving more and more to the right, and you can do more and more of that simulation. And as you know, one of the bottlenecks that has been to how accurate is a simulation, it's a simulation by definition, it's not completely accurate, has often been bottlenecked by the amount of computer that you have. If you're solving the Navier-Stokes equations or doing these simulations, if you want it to be really accurate, you want to do these massive simulations on billions of cells. And with something like Siemens Simcenter STAR-CCM, moving to the GPU has enabled to go to that next order of bigger, more accurate simulations. And I think that's helping many of these customers that you see on the screen here to really go down two angles. So one, if you take something like BMW, I think it was around 2.9 times lower cost. But the other thing that you see is just the ability to do things faster. And you can trade off between those two things. So it's been fun collaborating with you and Siemens and enabling these sort of customers to do bigger and better things. So can you maybe tell us a little bit about why do the companies do these type of simulations? What are their expectations? How much time does a calculation usually take? Yeah, well, in fact, maybe if we go to the next slide, I mean, this is a good example of the sort of trajectory that people have been getting in terms of the speed-ups. If you were to go on let's say, a CPU, and you're taking like 15 hours to do the simulation, what's been incredible is that every year that's gone on, without you doing anything, just by adopting the latest NVIDIA GPUs, that has just kept going down and down and down. And as I said, that has enabled people to do much bigger simulations. But I think one of the topics that's maybe a bit popular, topical here is also around AI. If you want to be doing AI and training large models, you need lots of data. And so what we've seen now is that a lot of customers are really focusing on what CFD code can give them the most efficient way of generating this data. And I hear very clearly that with the Siemens Simcenter STAR-CCM Plus GPU version, that is giving them that computational efficiency to generate this data. So I think this
plot is showing that the simulation time went down from about 15 hours per day on CPUs to about 3 hours. What does this mean for a practical design of, let's say, for a car? What does this mean for engineering team or for the design team?
Well, I mean, I used to do this for a job earlier in my career, and I'm sure you were the same, where if you come into the office, if you click the button and you get the result back 15 hours later, essentially that bottlenecks how many designs you can go through, and you essentially have to wait the next day to get a result.
Right.
Whereas if you can get it in 3 hours, you come into the office in the morning, you run the simulation, maybe grab a coffee, have a chat, think about something else, and then by lunchtime the result's back. And then you can simulate another one, and you can look at it before you leave, and then you submit another one. So your productivity goes up by going from that overnight to what is a morning or an afternoon.
Yeah. So what you're saying is with 3 hours, you can, within a day, you can do few iterations, improve the design, and see how things are going.
It's productivity, right? I'm sure if you're here as a business leader, all you really care about is productivity. How can I help my engineers to do more? And I think one of the things I've seen is your engineers are your most precious resource. So how do you make them more productive? And reducing the time it takes them to get an answer back is only a good thing.
Yeah. Neil, you mentioned AI, because I think there are implications there as well. And maybe the way you're mentioning AI is in a little bit different way, because you can use these results to train models that can be actually even much faster. Can you tell us a little bit about that aspect?
Yeah, absolutely. I mean, what's really interesting is this use of AI to develop surrogate models, which has also been a new feature in Simcenter I saw, enables people now to go from what would take hours or days to real time, to seconds. But the caveat is you need data. And so this is where there is that close coupling. So it's not a large language model like you would use in a chatbot sense. That's a slightly different thing. We're talking about training a neural network based on prior simulation data, and essentially how good that model is how good the data is. And so that's why AI is not a replacement for traditional simulation for something like CFD, but actually a close symbiotic relationship.
Okay, so just for my curiosity, how many simulations are usually needed to train an AI surrogate model? Do you have an idea?
Well, it's kind of interesting because actually nowadays it really is dependent on how broad you want your use case to be. So you may be able to get away with as little as 50 cases and train a model. But then you may only be able to do a specific, let's say in a car, a certain type of car. But you could extrapolate that and say, well, I want to train my model on all my sedans and my SUVs and my convertibles. And then your model would be able to generalize across much more. So it's a little bit use case dependent. Yeah. But it's certainly an exciting area that is, again, driving down to what is the most efficient, computationally efficient, easy to use, accurate code. Siemens is
and maybe related to that, something that always is interesting to me. I mean, can you, when you're doing these AI surrogate models, can you do it on any car, or as I would guess, so let's say if you have an SUV, then you have a series for SUV, a different model for sedans. I mean, can you
absolutely
talk about it?
I mean, the good thing is most of these car companies obviously have lots of, and by the way, this is not just cars. I guess we come from a car maybe background a little bit, so we like to talk about cars. But actually, probably we should move to the next slide because that might show also some of the other use cases. You could absolutely generalize across different cars. But one of the things is this AI technologies, AI physics, what we call NVIDIA, is actually also very applicable across many industries. And that's why it's been so important that the GPU acceleration has gone from being initially focused, let's say, more on incompressible, like automotive applications, and now going to hypersonics, to machinery, to sloshing. And so now you can simulate almost any application with the GPU version, which then also opens the door to almost any application on the AI side. Right. So it's been good to see.
Yeah, and I assume you're saying that because when you're the process of porting a simulation tool to the GPU it's a process. It requires a lot of things that need to be done. And if I look at this slide, I mean, of course, as you said, we start with incompressible aerodynamics, but then we add compressible, thermal, particles, multiphase flows. So I assume that's what you see.
Well,
right,
I mean, you know, not to belittle it too much, but essentially now, for most people, there isn't much you need to do. You need to go and buy a GPU from your favorite location that sells NVIDIA GPUs, whether it's on a CSP or from an on-prem provider or a SaaS provider, and then switch to the GPU version, because actually most of the hard work has been done by your developers to port the code.
Right.
Now you just take the GPU version and run your simulation. And I know it is literally as simple as that. I've seen companies literally switch from the CPU to the GPU version and not really have to change anything, and then just get these big speed ups. So it's this is, I guess, the value of the partnership between Siemens and NVIDIA, that behind the scenes we're doing lots of work together, so that end customers shouldn't really have to do much. Ideally.
So one question is about GPUs. I think people are going to have a question, where can I access them? I mean, do usually people acquire their own GPUs, or they access them on the cloud by a provider?
Yeah, I mean, it's completely dependent. We see very different things. Sometimes the value is through the CSPs. You know, we work with all of the major cloud providers and NVIDIA cloud partners. On-prem, you know, the great thing is that it really is now become a great ecosystem where NVIDIA GPUs have really tried to speed up in all ways. So wherever is your favorite place to get
them from. So it's you can get GPUs wherever you want them, right?
Yeah.
Okay.
But how about you? What's been your biggest, you know, over these past 4 or 5 years? What have you seen as really change thanks to this sort of accelerated computing?
Well, it's I think the two things. One is that everything is moving so fast. I think the porting of simulation tools on GPU suddenly are happening really fast. I mean, let's say we have a period of 4 years. We pretty much ported the entire STAR-CCM with all the capabilities on GPUs. I would say that would be a surprise, maybe even 10 years ago. So it's, I think that talks a lot about the technology that you provide and enable. Second, I think, you know, to have a full-blown aerodynamic simulation of a car in 3 hours, that's still, you know, I still remember it was taking like a week or days. As you were saying, like in three hours, this means I submit a simulation, I have a coffee, and I look at the results. And the last thing that is really interesting is what is happening with the surrogate models. In principle, some of the things should not be fully possible, but they are, and they're working, I would say, very, very well.
Yeah, absolutely. And I think maybe if we switch to another nice visual.
Why don't we do that?
What's the other thing? Computational fluid dynamics, color for directors, isn't that the other name?
I've heard many versions. The color for fluid dynamics was definitely a very popular one for a long time.
I mean, we joke, but the key point is air is invisible. So the reason that we focus so much on visualization is because the whole advantage of doing CFD is that compared to physical testing, you can actually see what's going on. So there is a reason why we show pictures.
Yeah, so I think it's, you know, you said color for fluid dynamics. So I would just like to say that, like 20 years ago, it was common that people would say that. And the reason for that was that when they saw a simulation, they expected that it's going to be less accurate than experiments. About 5 years ago, that has changed, and you could start using CFD to find mistakes in wind tunnels, and so on and so on. And I think at that point, I think CFD is CFDs, computational fluid dynamics, right?